Hi guys, in this video we'll be looking at the Picard approximation. So let's consider this question: x prime of t equals x of t, x of 0 equals 1. Using the Picard approximation, find a formula for x subscript m of t. The b, we find the limit of x subscript m of t where m approaches in an infinity for some fixed t belonging to real numbers. Now, what we need to know about Picard's approximation that it makes use of integration. So the first thing to do is to first integrate. So we integrate the function given to us here, this differential equation. So we're having the integral of x prime of t equals the integral of x of t. Now, the condition, the initial value given to us is from 0. Now, it will be from 0 to a certain value on the t axis. So since we do not know the upper limit, we assume it will be a t. It will be a t. So we have 0 which is given to us and the t. So we have the same thing here, 0 and t. So we can use dt as for here dt. Okay. Now remember from the previous video we said when we use t, we need to change the previous independent variable we use. So we have the integral of x prime of, to differentiate the t from this here, we change this to another variable, so we use s, so ds. So 0 to t equals the integral 0 to t x of s ds. So note that they are just the same, it's just a variable that is changing. So now solving these, we'll be having x of s, okay, on the value need to be evaluated on this limit, and this will maintain this because this is a function. It will be a function that we don't actually know how it behaves, so we maintain it like this, okay. But since it's in the function, we can write it in another format. We can write it in another format by saying f of, it's the function, the x function is depending on s, so we have s x of s ds. So ds is the same thing. All right, so this, evaluating this, will have x of t minus x of 0 equals the integral f of s x of s ds 0 to t. All right, now this x, this we can make the x of t the subject, the function x of t the subject. So we have x of t equals x of 0 plus the integral f of s x of s ds from 0 to t. So here we have the Picard approximation, but we need to solve it. We need to find a formula for this, okay. So we need to find a formula in this format following this. So in this case, what we do is, since we are to use, okay, let me go up there. Since we are to use x sub m of t, okay, so we say for x sub m of t, okay, we make m to be integers, a set of integers. So m should be a set of integers. So we have m equals 1, 2, 3 and going on. So this will be, we just got the same, the equation that we've had down there. X of t equals x of 0 plus the integral f of s, x of s ds 0 to t. Now from the condition already, x of 0 should be 1, and that is an interval, okay, so that should be 1. There's a condition given, so it should be 1. So we have x of t equals 1 plus the integral from 0 to t. Now this will stand for a particular function with respect to the x of t here. So in that sense, since the sum of this interval plus the function here, the value of the function here should give us this, so that means that the function here that will be here is a previous function of this. It's an equivalent previous function of this. So that means if this is m, then this will be as m minus 1. So if this is xm of t equals 1 plus, then this will be xm minus 1 of t. Oh, sorry, s. There is an s. ds. So that's Picard's approximation. Okay, so now what we do now is just to find the values, to find the corresponding values of the function for each of the integers starting from 1. So we'll be having, when m equals 1, so we'll be having x sub 1 of t will be equals to 1 plus the integral 1 minus 1 will be 0, so x sub 0 of s ds from 0 to t. Now we know that x sub 0, we know it to be 1. From the question, we know it to be 1, so this will be 1. So we'll be having 1 plus the integral, okay, but we know that x sub 0 subscript 0 of s equals x. We know that x subscript 0 of x equals x of 0 equals 1. So that means here we'll be having dx. Okay, so when we integrate this, okay, so we'll be having 1 plus the integral of this will be s, so 0 to t, so it will be s 0 to t. So this can be simplified as 1 plus t minus 0. So you'll be having 1 plus t. So that is for x sub 1 of t. So we do the same for when x equals 2. So we'll be having when m equals 2, when m equals 2, to be having x of 2 of t equals same thing 1 plus the integral 0 to t x sub 1 of s ds. But we know that x sub 1 of s equals 1 plus t. Okay, so we do have now 1 plus the integral 0 to t, so 1 plus, so now it will be s. We use s since we are using s as the function, the independent function. So we have this. Okay, then we integrate this. So when you integrate this, we'll be having 1 plus integrating s, you get integrating 1, you get s. Okay, s integrating this, you get s power 2 on 2. Okay, so you close, then you have 0 to t. If we are to substitute the value, substituting the 0, this is a constant, so this stays on its own, so we have 1 plus, but substituting the t, you have 1 plus t squared on 2. The 0, everything tends to 0, so plus 0. So this will be your equation 2. Do not worry about simplifying, just leave it. We are trying to check the patterns. Okay, we use the pattern, is very important for us to create a formula. Alright, so the next thing we have when m equals 3, it's better to insert 3 values, to insert for 3 different integers, so that we know we get 3 different values, so that we can create a better and appropriate pattern, at least 3. So we have x of 3 of t equals 1 plus the same thing, then integral 0 to t x of 2 of s ds. But we know that x of 2 of s of 2s equals, which we have up here, 1 plus t square on 2. So this means that we'll be having 1 plus the integral 0 to t, so put in bracket 1 plus, so we use s plus s square on 2 ds. So this should be equals to 1 plus, so we have integrating here, we have s plus this will be s square on 2 plus 3, so this will be s cube, then we'll be having 2 already, then times 3, so the evaluation is this. So we having this will be equals to 1 plus t square on 2 plus t cube on 2 times 3. Okay, so we can now create a pattern. By observation, we can create a pattern now. Okay, so this can assist us to develop a formula. So we introduce a technical term which we say by induction, so we can induce the formula. So by induction, so we'll be having xm of x m of t will be equals to, it follows a pattern, so we can create a pattern. As you can see here, the first is 1 plus t, the second it's moved to 1 plus t, then there is an addition of t square on 2, then the third term there is an addition of t cube, and the product of 2 and 3. So we have, you can see you have 1 plus t plus t square on 2 plus t cube on 2 times 3. So that means that the next one will also be t exponent 4 on 2 times 3 times 4. You may try it, you may try and see. So plus, so it will continue like that till where we have the m. So we'll be having t exponent m on 2 times 3 times 4 times to the point where we have m minus 1. M minus 1 times m, to the point where we have something like this. Okay, so if this is the case, then we can introduce a factorial. So we're having x sub m of t, which will be equals to 1 plus t square on 2 plus t cube on 3 factorial, because 3 factorial will give us this, then plus up to plus m factorial. So we can induce this and arrive. So this is the formula. We can write this as a formula, or you can introduce since it's a sum, it's a series. Okay, since it's a series, we can form a sum notation. Okay, so if this is 2 factorial as well, and this will be 1 factorial, and this will be 0 factorial. So that means that there is a connection between the numerator and the denominator. So we could say that the power here, the denominator the denominator is actually the power of the element of the numerator. Okay, so the factorial value, the factorial position, or the factorial element of the denominator is actually the power of the numerator. So here we have t exponent 0 here. Here we have t exponent 1. Here we have t exponent 2, t exponent the 3, and t exponent the m. So that means that we can create a sum notation by saying the sum of all the elements. So see, t is constant up, and the value down here changes, so we can use a variable r factorial. Now that r down is the power of the elements of the numerator, so r exponent r. So if here, if you're looking for the first element, so it will be 0 0 0, so you get 1. So since it's starting from 0, then that means that r should begin with 0 and should end with a particular value, let's say m or n. So you can use n, or if you can use n. So this will be our formula for the first one. Then the b, taking the limit, the b says limit of m as limit of the function as m approaches infinity. If the values should continue repeatedly, if you should repeatedly add all this value to a certain unlimited unlimited series, then that means that it should be getting closer to an exponential function. So we have limit of x m approaching infinity for the function of x sub m of t. That means that this should be equals to e exponent t. E exponent, the constant value, the constant element, the constant numerator element. So t. So e exponent those t, and that is that. So that is the value. Thank you. Don't forget to like, subscribe, and send more questions.